All right, howdy folks. Welcome to NESnet Day 3. We are connecting the NES to the internet. We've got progress on a few things since last time. Well, last time I had a bug, but anyway, we got our cartridge. We got our ESP device, and right now I think it was off stream that I cleaned up some of the GPI, or no, I didn't get this working last time. Yeah, and then I cleaned it up. So I had a problem and I couldn't figure out what it was. Well, I was being dumb. The problem, in my effort to cover everything, this was my code. I had a copy paste error from up here for when it's not enabled to keep whatever you previously had. Well, yeah, I was latching the mapper register value, and that it worked when I ran a very small number of things. Oh shoot. I need to fix that. Forgot about the command line argument stuff we were doing. Broke everything. All right, let's try that. What script is it running? Oh. Too many things going on at once. All right, how about now? I think that's what we got this tab for. Got a new NESnet script. Okay. Try that. So I think this is going to write a sequence of values, and with our bug fixed, it should, we're sending UDP packets of the current GPIO state. So it's writing 0. There we go. We got 0, 1, 5, 8, A, F, which is what we did. We wrote 0, 1, 5, 8, A, F. And the INL retro was able to read it back. So it wrote 0 and then it read it back. So the and of course this doesn't actually matter. You don't actually need this else case. Synthesis tool can figure that out on its own. Our bidirectional buffer, so when we have a read from 5,000, everything's able to, the INL retro and or the NES is able to read back this register value. So next stuff, let's see. So this is our packet right here. This is our Arduino code that's just reading each GPIO and then constructing this message that it sends every 3 seconds or whatever it is. So what we want to do next is, instead of just reading right now, all 4 of these GPIO are direct outputs from the CPLD to the ESP, these 4 pins, 0, 1, 2, 3. So we want to read the data out serially. And I put a lot of thought into some different stuff on the protocol, on how we're going to get data back and forth. I don't think I'm actually going to get into this stuff today. I really just want to be able to I suppose I can get rid of this, huh? I want to get the shift register working. None of this stuff. I think what's going to end up happening is we're actually going to need to decode another register. So we're going to have to change the plans a bit. But yeah. So our serial parallel register, this is what I think things are going to look like, but we don't really have to get into it that far. All we really want is we want to update this register, or ESP reg. So it needs to be parallel writes and serial reads and writes. But I think the ESP is going to... We can't just have... Oh, let's take this. So I... Oh, here it is. Let's clean up some of this code here. I have... This is decoding when the CPU is reading from 5,000. This is what we've got to do here. But this isn't actually going to work because... So here's the problem. We can't... So when do we want to have parallel writes? Let's just do this for now. This is a little bit easier to follow along. So this will be a... If progress write is required to be low, so now we have a new signal that goes low when the CPU we're still getting... Yeah. It's still chugging away. So this signal goes low when there's a write to 5,000. So we could change this instead to go like this. We'll change it to pause edge of write 5. So when that, at the end of the write signal, because this is an active low signal, so it's going to go low when there's a write. At the end of the write is when we'll latch the data. So we're doing all of this checking effectively here. So we just say anytime there's a positive edge of this, we latch the data, which should be fine. But we need to be able to modify this register even, or not only, we have two ways of that we want to do this, right? So we got an 8-bit register, I think it was 8 flip-flops in parallel, we'll want to be the NES to be able to write to this via parallel. But then we want the this to go to the ESP, this to come from the ESP, and this is going to be a clock from the ESP. So this is actually going to be ESP data out into the shifter, out of the ESP into the shift register, out of the shift register into the ESP. So this is, if you think of the ESP as the master device here of the serial register, this is commonly referred to as MOSI and MISO for master out, slave in, master in, slave out. So right now all we have is this portion here, and we also happen to have an output with a tri-state register for the NES, so we can read this out parallel also. But that's all we have. So we effectively have this problem where in this looks like it's synthesized just fine. We're using 24 macro cells total. So if we just think about it in a, this is where you have to think about this in terms of hardware, because you can't always just write some code and it'll synthesize to something that fits in the device you're programming. But this is like the behavior that we want, right? So we could also say on the pause edge of ESP clock, we have to define the signal, which pin we want to be as that. But we could say if write 5, if that signal's low, right? Because on the pause edge it will have just been low. We want to latch the data. Else we want to shift serially, right? So the ESP register 7 through 0 will be, so this is just, how do we tell which clock edge we got? Well, if we think of these as an asynchronous load signal, and this is happening, I mean, this isn't perfect, but this might be where mind goes to initially. So what are we going to do? 7 through 0. Which bit do we want to come out first? The way I've drawn it here, it kind of looks like we're going to have, I'm not really making it overly specific, but think of this as bit 7, 6, 5, 4, 3, 2, 1, 0. So bit 0 right now is the ESP can read bit 0. We're going to shift everything. But okay, so bit 0 is going to become bit 1. So that covers the last 6 bits, but the first bit is going to be ESP the MOSI signal. So bit 7 will become MOSI, and then bits 6 through 0 will become what was previously bits 7 through 1. But I was kind of tinkering around with this. This probably won't synthesize. Now this might synthesize in a more capable device. FPGA or something should be able to do this. Oh, where did I missed a semicolon or something? I think we're going to get an error. Does not fit in a standard flip-flop or something. Oh, we don't have this variable's ESP clock, so let's do this. Let's figure out let's rename these into what we actually want them to be. Or we're gonna have to go fix our constraint editor, but that's okay. So I think I want, trying to decide how I want to assign these pins. To some degree, I don't think it's going to matter, but this flash pin needs to start up pulled high, and I think GPIO2 has to also. So if these are effectively inputs, to the CPLD, right? If only the ESP is ever driving these, then having pull-ups on these signals will ensure they're high at power on. So let's try to make these two signals our outputs. So 0 as SCK and 2 as MOSI. So this will be input ESP we're gonna have to get rid of these. Let's just go ahead and assign all of these. So we're still going to have this as an output. Let's make one MISO and have this one be like a interrupt pin. Our constraint editor is not going to know what to do with that. Comma. Yeah. Give me the constraint editor. I want to fix it. Oh, I think it's because we said this is ESP MISO, and this is interrupt. Okay, I think that'll fix it. What the heck? ESP clock. So you don't know it. Oh. Can't make up my mind on what to call these signals. It's not fast. Yeah, it does not match standard. Got that error that I was expecting. It does not match standard flip-flop. I thought I was going to open the constraint editor anyway. So we can only really have one clock signal. So here's my thought. This is we're not going to be able to, because this is effectively, we have an ESP, the way I have it drawn here, we have an ESP clock, but then we also have a parallel load signal, which is effectively acting as a clock signal of sorts. These flip-flops don't have asynchronous set, reset, or loads. So we could look at the data sheet, but that's what I understand. So we need to generate our own clock signal that captures all of these cases. Now it's gonna get a bit hairy, but we effectively are controlling both the ESP clock from the ESP side, and we can make some rules about when the NES is allowed to write to this register. We could also come up with some sort of enable bits inside the register or something, but just to keep things basic, let's do this. Let's assume that our default state of ESP clock is going to be low, and then whenever we want to clock data in and out, we'll take it high. So we get I don't know whether we want to use the rising, the positive edge, or the falling, the negative edge yet. We can pick that ourselves, because it only matters of when the ESP presents data. Does it have to present it here, or does it have to present it here? Well, we can kind of we can decide that for ourselves, because we're doing all of the bit banging from the ESP side ourselves. But for the 6502, let's say we have a clock signal And then whenever the effectively this write to 5000 signal, here I define it as a active low signal, but thinking about it, it's a little bit easier to think of it as an active high. So if we had these two clocks and this was effectively write to 5000, right, we could just OR both of these clocks, send them into an OR gate, and then that's our clock. This becomes a shift register clock or a 5000 register clock. So here, we could just OR these, right? And then what are we going to get? It's just going to be, we'll get anytime ESP clock comes in, and then my timing's not aligned here, but you get the idea. If we just ORed these two signals, we would get something that looks like this. So if we can do this, there's some assumptions that we're making that, because part of the thing is like, well, what if the ESP is shifting data and all of a sudden the 6502 makes a write, and time wise it's probably a lot longer, even if it wasn't though, right? And then you ORed these, you would lose one of your edges. So we'd have like 3 clocks going on, but only 2 of them would come through there, up until that point anyway. So we're gonna have to come up with some rules to prevent that from happening, or some sort of protections. But if we assume that they don't collide, then our clock signal can be that simple, to where we just OR them. So here we have the ESP clock coming through, and here we have the 6502 clock coming through for the write. So let's try that, and then we do need to know. So we can't. That gets our clocking how the flip-flops need it. All we need then is some sort of signal. Is, are we doing a parallel load, or are we doing a serial shift? So we'll have to generate this signal, but we'll have something like a load signal, which will be, we can think of, I don't know if it's going to be active high or active low, but we can think of it as, and actually probably won't come until, it'll come at the same time as this. I didn't draw it very well. The edges will be aligned to the 6502 write signal. Because we only have so much that we can do here. That we're limited to signals that we can generate from the cartridge connector. But we already had this signal, right? So going back to, well, do we want to use positive or negative edges for our flip-flop? Well, once we get this far, to some degree our answer is kind of, we don't really have much of a choice. Now we could always invert everything and then use the other clock, but do we want to use the first edge or the second edge? to clock data for this shift register they're writing here. Well, the thing is, from the 6502 side, the parallel port data won't necessarily be valid at this first edge. We're using part of this write signal. Oh, we don't actually have M2 in here. That could be a problem. We forgot that guy. Yeah, that should be in there. So if M2 is high, did we? I think I've got it back here. So the M2 is basically the clock signal of the 6502. It's hot, so this is basically the beginning of the cycle. M2 goes low. It's the end of the previous, the beginning of the next. When M2 is low, the 6502 is setting up all of its address lines, the read-write lines, and if it's a write signal, it's getting ready to set up the data. But writes don't actually, and if it's either a read or a write, whichever device is trying to get the information, it doesn't actually latch it. It can't know that the data is valid until the very end. So this is, we really only want to pay attention to ROM select and everything else when M2 is high, and then latch our data at the very end. So that's why our read and write signals should include M2, and also ROM select being high doesn't actually tell us anything unless M2 is also high. Anyway, so we have those included in there now. But that tells us, well, so based on that knowledge, this is when we actually have to latch the data. So if our clock has this polarity, it's actually the falling edges. And we could use this load signal. It's also a clock, but we're ORing it into our clock. But with this setup, we can say if load is high on this falling edge, then we're going to do a parallel load. If it's low, then we know it's an ESP. So that's how we tell the difference based on this signal that we generated. So let's do that in a Verilog now. So we have a write to 5,000. So we're going to do always at neg edge of we'll call it SPI clock. We have to generate SPI clock, but when that happens, so if write to 5,000, it's actually what I drew here except inverted, which is fine, right? So load parallel is going to look like that. So we can just, if that signal is low, we're going to do a parallel load. So the ESP register is whatever the CPU data bus is, parallel, else we're going to shift it. So we have to actually generate this clock signal now. I think we can just do I forget. I'm used to doing it using always blocks, but I think what we can do is instantiate SPI clock here and then do assign SPI clock equals thing of it, active high clock is kind of a funny way to say it, but it's normally low. And it just goes high anytime that we have a event, either serial shift or parallel load. So ESP clock, yeah, that's what we called it, which was that pin. And we actually have to invert right I think we can do that. Oh, we not and or. So let's see if that'll synthesize for us. We also have to fix our constraint editor. Oh, it must be nettype. It isn't. I don't think that's actually how you. I think you say wire. Expecting end module. What? I think that's how you do it. That might be. Getting somewhere. All right. So we reassign these. Give them meaningful names instead of 1, 0 through 3. So clock is going to be 0. So ESP0 was pin 15. So clock is going to be pin 15. I have to go and fix these, but let's just get the pins right. ESP1 is going to be MISO. So ESP1 was 14. We didn't actually assign that one to anything. Oh, I thought we did though. Yeah, ESP MISO is assigned right there. It should be there somewhere. Here we go. So this one's going to be what, 14 I said? Yeah, ESP1, 14. 2 is going to be Mossy. So 2 was pin 4. So Mossy is going to be pin 4. And then interrupt pin is from 3. So ESP3 was pin 40. We didn't actually do anything with that pin. Or wait. Yeah, we did, didn't we? Yeah. It should be there. There we go. So pin 40. We want these to be these are signals coming from the ESP. They're just 3.3 CMOS. And then ESP MISO and interrupt, these are outputs. Just we'll have CMOS 3.3 and we'll have a slow slew rate, and just always do slow because we're not running that fast. Not pushing the limits of this silicon. All right. Save that. I think I might have to actually delete these. Let's see if we don't though. Yeah, I did not like that. Let's just double check these before we. So 0. Is clock. So ESP0 is pin 15. And now ESP clock is pin 15. Okay, ESP1. So let's delete this one. ESP1 was pin 14. And now MISO is pin 14. MISO pin 14. Yep. All right, delete this row. Now they're ordered in pin number, so it's right next to it. ESP2, Mossy. Yep. Delete row. And ESP3, interrupt. Yep. Delete row. All right. Save that. Now let's try. Okay. What are we looking at for logic consumption? $25. That only costs us an extra macro cell. Because really we're just giving the current macro cells more features, but I don't know what actually cost us a macro cell there, but whatever. There's some logic. Okay, so I think, hey Quitsu, yeah, we're doing Verilog, man. We We are programming the CPLD with a shift register so that our little Wi-Fi dongle, ESP01 Wi-Fi chip, can get so that 6502 can talk to it. So let's try to program CPLD here. Did it actually generate a JEDEC? I think it did. So if the shift register is working, now all we have to do is bit bang a SPI interface from the Arduino. On the rising edge, be sure to latch the clock with an ORed flip-flop NAND gate, but a SPI clock rate of 200 Hz shifted left 8 times. I don't know what you're saying. Yeah, I think you're. That sounds like me talking, is what it sounds like. That's what we're doing, yeah. Okay. What's build time on this? Today? Yeah, just fitting in. Exactly. Precisely. Okay, so I think that's right. Is it taking us 3 minutes to get this far? Yeah. So now we're stepping back into software world a little bit, bit banging. So software twiddling bits. Yeah, I understand edges at this point, which is more than I understood 20 years ago. There you go. Yeah, flip-flops like to operate on edges as compared to latches, which are just active high or active low. If the signal's high or low, then it latches what you got. The real reason that the logic made the switch from latches to flip, the real benefit of the flip-flop, the edge sensitivity, is you can have glitches in those signals, a blob of combinatorial logic. There's some propagation delay in there, and you may get bad signals. You're not gonna get the right answer for some period of time. So if the flip-flop only pays attention at it, you can have a clock and say, I want you to only pay attention, only do your thing on this very specific time. And that's the real reason for it. So this is a Wi-Fi client, i.e. NES sending and receiving, or a server. Both, well, able to be both. And what's handling the 802.11 and all that. So it's actually my goal, and it kind of depends upon how far people want to get, but my goal is to effectively have think of them as registers inside the mapper, but really it's more of think of it as like a variable. So have a set of variables that are in the mapper. There'll be a specific sequence on how to write to those variables, but they could be put into a subroutine or a macro or something like that. But so there's a variable inside the mapper, which actually ends up existing on this ESP chip. So ESP8266 is a, this is what ours looks like. It's just this little chip here. So this thing handles all of the 802.11. It does everything, all of the Wi-Fi side for it. We really don't have to care too much about it. And we have it. It has, there's libraries for this thing to where you can just connect to a server and send, or connect to, you know, so these two things could actually connect to each other. Just need to, so one idea I have, like the most basic, I don't know, my internet knowledge is weak. I know enough to get myself in trouble. So the ESP itself handles the IP and the TCP part. Yeah. So this is my code that's running on the ESP right now. It's actually written for Arduino because there's a whole library for Arduino for this thing. But right now I'm sending UDP packets. We also did some demos with TCP packets. There's some libraries out there for this thing for WebSocket as well. To, you know, gain the benefits of TCP with a little bit better latency, and it does that also. Yeah. And this thing, the best part of all, right? Because this thing's just made by some Chinese company. These things are like $1. This is individual quantities. $1.20 for this thing. You can get these little modules as well that have more GPIO available. Yeah, so this thing's cheap enough where you could put it in the cartridge and you could publish a game using it, and it's not like, I mean, you could have some, you know, power pack style device that's meant to be used for all kinds of games, but you know, in terms of publishing a game, it's cheap enough to where you can just put it in every single cartridge. We've got to put a little bit extra hardware in the cartridge so that the NES can actually talk to this thing. But I'm trying to make it work in a 32 macro cell CPLD, which is the same ones that I use for the simplest MMC1 boards. I have other ideas of getting fancy and trying to use the kick as a coprocessor to handle the communications to make it even cheaper, but we gotta get working first before we get too fancy. Anyway, yeah, so kind of so it's basically just a little microcontroller, and we are trying to get by with only 4 pins. So you've got options here. Now, right now, all we do is in our code, I have my network, NESnet guest, and then my password. So that's programmed into the device, and it just boots up and connects to that. But here's the thing. This thing can act as a wireless access point as well. So we can set it up to where when you power it up, it acts as an access point, and we could, you know, give it some default password. You can use your phone or computer or something, scan for wireless networks. It'll show up as an available wireless network, the NESnet cartridge. So you could connect to it, and then it can host a little web server. You go to the IP address and it says, hey, what's gives you an interface with the chip without even having the NES or something like that. So you could use your phone to give the cartridge your wireless network and password, and it could store a handful of those and automatically connect to whichever one's in range. Now you could build a interface with the NES as well, right? So you could have the cartridge scan available IP networks, and it, typing in an address with a controller alone would probably be a pain. So that's kind of a nice feature that you could do using the access point. But there's lots of different ways to solve that problem. Yeah. So what my goal is, so I'd like to get two of these things connected peer to peer. And my idea of the variables kind of abstracts everything network away from the NES programmer. I mean, they can get into that if they want, but with these variables, the ESP is just maintaining these variables. They'll be, half of them will be read only and half of them will be write only. So when basically it's a copy of the other device and the current device. This C code is running, compiled and running on the ESP. Other thing that's nifty about this thing is when you I don't have it running right now, but once this thing's connected to your network, right, it has an IP address. If you are on a computer that's on the same network, there's web updater that you can use and just go to the URL of your device, and it presents this little update. So you can upload a new binary and do over-the-air updates on it. So it kind of become like you can do everything through the network. But yeah, so it's pretty slick. And this chip's been out for a while. August 2014. And then back in 2016, they released a successor, the ESP32. This guy is a dual core. This thing's a beast in comparison, and I think it only costs like an extra $1 now. But this thing also has Bluetooth. So if you wanted to like connect to Bluetooth keyboards or something like that, you could do it. But just starting basic with this guy. So let's see if we can get serial data out of this thing now. Make sure that it's communicating. I wonder. So it's not actually powering up. I think we're having issues with the pin assignments. I have pull up. These are supposed to. Oh, register power up none. Why is register power up none? Oh, because these are new signals. Let's do register power up. Set. Now I don't. We tried to set these up. All right, take care, man. Yeah, this is my Friday project right now. So we'll be. Oh, you are. You got any details we can check out? Are you using the ESP as well? We need internet connected everything. ESP32. Cool. Yeah, that guy is a beast in comparison. Oh, he is. I didn't know that. I'll have to check that out. So we're having issues with the pins not being high at startup, I believe. Yeah, 240 megahertz. This thing nominally runs at 80, but you can overclock it to 160 and it doesn't seem to care. Yeah, I'll have to go check out No Cache's project. The thing that's most appealing about the ESP32 is the Bluetooth. That's nifty. And the other thing is if you want to have some legit security, it's got enough processing power. Oh, okay, cool. Yeah, no rush. Today's not going to be an overly long stream like past ones. I've got to take off, but or if you want to share it with us, well, I won't be around next week, but the following week. If you're unable to get something to show us today, you can show us next time. Something tells me it's not gonna go. I think it normally like just make sure I didn't break something here. I might swap the pins around. There it is. The LED like flashes for a split second when it first powers on. If it's not in boot mode. Oh, even if it seems to do it either way. This thing shouldn't be going in programmer mode. Does not seem to be. Maybe it is. Yeah. Get my multimeter here. It's going now. .3, 3.0. But if we just power this thing up, it does not. So it doesn't seem well, maybe let's just switch the signals around. It seemed to work okay when the CPLD had all these as outputs. I switched the pins that I thought needed to be in a specific state as inputs to the CPLD, and thinking that the pull-ups would be good enough, but maybe the pull-ups are too slow. And so it's best to have these as outputs and starting up high. Just want to make sure I don't get these all backwards. So, or maybe we can take notes here. So 0, 1, 2, 3. Zero is our flash. I think 1 might actually, or 1 is transmit. 2, I think that one actually matters for boot as well. We did we went clock, meso, mosi, int. So clock is pin 14. Oops. Yeah, wait. Yeah, so we're not going to do them this way, but we went clock, pin 14. Meso, pin 13. Mosi, pin 4. And int, pin 40. But let's swap those around. So we want this pin to come from the CPLD and these to be outputs from the ESP. So clock, can't see that. This one is, let's change this one to interrupt. And this one to meso. So if we rearrange those in the constraint editor, mosi, we want to be pin 40. Let's order them this way. Clock, we want to be pin 13. Whatever, it doesn't like that because we're stomping on top of the pins that are available. We have 2 pin 40s though. You didn't care about that. Interrupt is pin 14. Miso is pin 4. Interrupt pin 14. Okay. Interrupt is 14. Miso 4. Mossy 40. And clock is pin 40. That's an invalid number. Yeah, because Mossy is 40. What am I doing? Clock is 13. Where is 13 being used? I must have... Dang it. Get mixed up. Going live on Twitch. Yeah, let's... Where's my... All right, let's go check it out. Okay, I'm on your channel. All right. There we go. Okay, got the ESP32 there. Oh, I can hear myself.
Just say something on the chat.
Oh. It's gonna show up on the... Sweet. So you got a little Twitch chat client. That's pretty cool. Vi Graytech was working on an NES. So what kind of flash cartridge do you got there? Is it your own design, or are you hooking it up to... Okay. Sweet. Very cool. Thanks for sharing that with us. You're a lot further than I am. So we gotta figure out what's going on with these pins. I got everything all messed up. Nice. Yeah, it'd be cool to see it. Oh, I didn't... I don't think I'm... There we go. Do you stream development of it as well? Yeah. Power. Yeah, that is a problem with the Game Boy. Okay, cool. Yeah, it'll be cool to see. I gotta figure out my pins because that might have been why we're having problems. Okay. So NAND, let's get this. Documented which pin is which here. So the first one, NAND CA. Actually, the first one was GPIO 0 flash. CA12. It's pin 15. NAND CA is pin 40. CA15 is pin 14. Pin 14. And what's the last one? CA16. Pin 4. Okay. Now, what's what? Four. Pin 4 is MISO. 4 MISO, that's right. Which is master out, slave in. We're assigning that to pin 2. Master in, slave out. Yeah, okay, so this is now, I want this to be a CPLD output and this to be a CPLD output. Pin 13 is clock. This is supposed to be 13. Why is CHR A14 assigned to pin 13? Well, I don't, it's gonna be bit banged. So it's gonna be software dependent on the, not really good. It's not gonna be a synchronous clock. We're just gonna bit bang it from the ESP side. So I don't actually, it's gonna be dependent, and interrupts and things like that will cause a lot of jitter and stuff. But the way I have the interface defined in my mind, I think we'll be able to make it work. So why did CA14 get assigned to pin 13? Did I mix something up? CA14. LX. Initially was using 8266. Oh. So sounds like you're more directly connecting things up. I've got some glue logic, so I'm a little bit more, yeah, okay. Which is pretty slick if you can get that all working. I mean, you already do, so that's pretty legit. I'm surprised. What are you using, Arduino? Or what's I can't imagine there's so much. Well, you got two, that thing's a dual core though too. Do you have a ROM chip for the Game Boy to execute off of, or is the Game Boy executing off of the ESP32? Pin 13. Well, that's what yeah, pin. What? What? That's not right. Pin 14. Why did I? There is a ROM for initial load most of the code into RAM. Oh, okay. Okay. I gotcha. Okay. Makes sense. So, I'm getting all mixed up here. GPIO 0 is pin 15. And GPIO 1 is pin 14. So clock is supposed to be 14, and interrupt is supposed to be 15. That's my problem. Okay. Save that. ESP is also not as fast enough, so use the A address and data pins for communication. From the Game Boy, you're saying? Yeah. Oops, I do not want to print anything. Yeah, I like your approach. My approach, I'm trying to more generically glue it on to any mapper. All right, let's reflash this guy. We've rearranged. I'm having a hard time keeping track of what I'm doing here. Rearranged the GPIO. So I think the pins will be high at boot and the cartridge will, or the ESP will boot from the flash. That's the problem that we were having as far as I configure. Oh, the LED's just on, which actually why is it low? They're supposed to all be high. Well, let's check with the multimeter here. Make sure these pins are high like I'm expecting. That's low. That's low. Why are those pins low? They're supposed to be outputs. Miso and int. Why did changing? We're supposed to start up a set. Why did everything break when I did that? Do the other pins, are the other pins high with their pull-ups? Why did that go low as soon as I took up? Let's try this. Let's go back to what we had. So 0 is supposed to be oh, wait a second. 0 is interrupt. Oh, because I moved them. Miso. So, int clock miso masi. All right. Okay. We can still use these. The logic will be broken, but it should be okay. So this is effectively the same thing as we should have had previously. All of our pins were high, and the ESP was booting from flash. Okay. Oh, these are not. I don't think those pins should matter, but well, maybe that's not going to go. So clock and miso. Shouldn't matter. Those are serial pins. It's starting up low again though. Set. Power up of those should be set. I don't know. Let's see if I have an old one in here. Oh, this one's a mapper register. Flash this one on there. That seems to be working. Yeah. I don't know. If I can get this thing it's not starting up set like I telling it to. Maybe I should. Yeah, as soon as it goes, it's so these. I'm gonna try this. I've got I'm gonna open so it's this project. Let's see if this thing has the GPIO starting up high like it's supposed to. It's like, how do you even troubleshoot that? Why is it? I guess try to go back and change the. We changed the SPI register. This might just be what kills me today. I just get stuck on this, and it's just the way it goes. That seems to be working. There it is. Let's just go with this project. I probably shouldn't have renamed the signals. I hate this. Okay, so let's do this. Copy this project from my NAS. And then I'll have a copy on local machine and use that. Now, close this. So eventually we're gonna need another, I think we're gonna need another address pin. And I think what I did is I disabled, this is actually on 256 KB flash. So I was gonna, for now, use GPIO, or use set. Anyway, so I don't have prog A18, but I have CPU A0. Now it's not actually wired on the card. I haven't actually modified the card yet. Maybe we should just do that. Although I'm running out of time. Let's just leave this. Let's do this. So this doesn't have our ORed in clock. And maybe this is so 2. I'm actually going to have this be master in, slave out. So I'm going to have this be bit 0. We'll just set this to bit 7 for now. This is eventually going to be ESP interrupt. I think this will let us clock data. The only thing is this, I don't have CPU A0 signals. Also, we changed M2. I don't think any of that stuff should matter. But let's just synthesize this and try to add M2 back in. Hopefully we don't lose our GPIOs being high at startup. So I shouldn't have any dependence on CPU A0 anymore. Errors occurred. Line 94. What's going on there? I'm gonna do this. Oh, I know what the problem is. I don't actually have, this is not a signal. 5,000. It said error. Where's my error? Oh. I think it's because I didn't, in order of. I need to have this instantiated before I use it. Okay, I think hopefully. I don't know why you're not telling me my error. Oh, lattice. killing me. Where is my error? Why? How am I supposed to? I think I know. Just make me guess my errors, Lattice. You tell me. Not happy, Bandit. Sometimes hardware development is just a bunch of head banging. All right, let's flash that guy. Flashing, flashing, flashing. The pin's not low. Okay. There it is. All pins high. Okay. Sweet. So let's do this. It's always we're not able to change the register. Okay. Nor did we really expect to, because the ESP is, there's a pull up on the clock signal. We have to take it low so that clock that that O-ring, right now, the ESP clock is just high the whole time. Right here, it's just high all the way across. So we need to update our Arduino code. What's what? Our 0 is clock on this assignment. Now I might want to change things around, but that should be fine. 0 clock and 1 as master out, slave in, Mossy. And then 0 or 2 is Miso. Okay. That's what we got. We haven't assigned, we haven't doing anything meaningful with this one yet, but we will. All right. So 0 is going to be clock. 1 is Mossy, Miso, interrupt. So let's set this pin mode to output. And let's set Mossy as output as well. And then set high. So how do you... So digital write. So let's do this. Int pin, or so SPI clock equals pin 0. SPI Mossy, Miso, 1, 2, 3. All right. So we'll set this SPI clock to output, SPI Mossy to output, and then digital write SPI clock low. And we'll do the same for Mossy. And then these will be inputs. So we start off as low, and the NES should be able to write to those pins. Let's just go ahead and build that. No, that's not what I wanted to do in Windows. So if we get that working, yeah, this is what we want. That's right. Then the NES should actually be able to write to those registers. I did too, didn't I? SPI Mossy was not declared. Yeah, it's right there. Oh, do I need to have these defines at the beginning? Well, hold on a second. Where's my setup? I think I want to put those at the top. What, Bandit? What? What's the deal with the order of these? Oh, semicolons. That's my problem. Arduino, you're so great at meaningful errors. Seriously. There we go. All right, so is it actually writing? It's not. There it goes. Okay. It's saying it's high. It shouldn't be, though. I'm gonna let Bandit out. All right, so why aren't our pins going low? Pin mode, output. I don't know. Are they actually? It would seem they are. Yeah. I don't know. Output low, output low. I don't know. Things are not going our way. Top it off. Having serial communication problems. And Arduino requires you to compile it every time. I think I'm gonna switch platform EO. I'm still gonna have this serial problem. I don't know why. Yeah, I can't even flash my... If I can't get this to work, then I can't program these things anymore. Why is it... It's not putting into program mode. Yeah, look at it go. Well, now it's... I wonder if they couldn't go low because the cartridge was taking them high. But they were... Oh, did we have them as... We had them as outputs, didn't we? No, we didn't. They're inputs. I don't know. We're just kind of getting nowhere. My serial programmer is not working. There it's going now. Oh, it just started going. Okay. Start talking. There it is. Okay. Working. Now, let's write to this thing and make sure we can read back. There it goes. It's not reading back properly. But we did change some bits. So, and I got another ESP flashing, seems to be going okay. All right. Why? So let's write FF. Where did we read back though? 0. Well, so we'll read. Let's just read, see what we get. FF. Let's try to write FF. Yeah, see, it looks like it shifted. So we wrote F, but then it actually shifted. And what did it shift? It shifted in D0. So I don't know how clean this signal is, but it's like both of these things are happening. That's what looks like it's happening. Or is our write not actually occurring? We just can't do anything other than shift. What if we try to write again? Look at that, we get 3F, so we're just shifting it. So our writes, this is never apparently true. I don't know. Part of the problem is our enable is our same as our clock. Now, let's try this. So let's just make sure that we can actually write. So we're able to write to it. This clock is working. But I have a feeling if we do this, it's not going to work anymore. And that's going to be a problem. On the falling edge, or basically the rising edge of this, at that time, the signal should have been low. But we're making some assumptions there. Stop working. Starting up low. Then maybe that's related. It's always 7E. That might actually be related to our problem that we were having before. Oh, you know what though? We also didn't get ROM select or M2 in here. Let's do this. Let's put those in there. Let's take this back out. because we actually want everything to be referenced to M2. M2 will be the first signal to change and cause that, give us the edge that we need. I don't know why that first read is FF. Blocked the first one for whatever reason. Maybe the ESP hadn't connected to the network yet and ran my IO, my init code yet. Anyway. So now that signal is referenced to M2, I wonder if that fixes things. That might have. Part of the thing is we're not actually running on an NES. It's my INL Retro and the microcontrollers controlling all the pins. I don't know. ROM select is being left high. The address, all that. Yeah, if we're not using M2 as a reference edge, then that might be causing everything to get crazy. So let's just see if that changes anything. That pin is just high. It's not gonna. It's always 7E. Huh. Yeah. Gonna have to think about that some more. That is not. So what if this, for now, what if the ESP controls whether a parallel write is allowed with the interrupt pin? So we'll say that's normally high, right? The NES can write to the SPI register. But when it's low, the NES can't. So let's try that. So we still have our clock, but instead of ESP int equals high, then a parallel load is allowed. Else, so when the ESP wants to, how we're going to control this interrupt signal, I'm calling it, it's not, well, it will be an interrupt eventually, but will change. But this basically allows the ESP to control whether it's parallel mode or serial mode. Now, we're driving this pin high. It's just going to be stuck there. We'll just say it's an input for now. All right, let's try that. I'm thinking about this being basically an open drain signal to where it's pulled high, but either device can pull it low. Blinked like I wanted it to. There, it's talking. Okay. Zero. 1. Okay. So now the ESP controls whether or not the NES is allowed to write to that register. Let's change and let's take that pin high. Let's make sure this, I don't know, we're having problems before. That actually... All right. Looks like that guy flashed okay. So let's try to clock some data out of this guy now. So we'll go ahead and leave those. It's just reading the pins and giving the output. Bit bang out data. So to do that, first we've got to take interrupt pin low, serial mode, then now it's actually the falling edge, toggle clock. So in reality, so let's do this. Int low. Now, which pin is our, well, let's do this. Digital read, SPI, MISO. So this is bit 0. And then at this point, we would read bit 1. Put this in a loop, but I'm just gonna say the heck with it. So this will be bit 2, 3, 4, 5. Might need a few of them. All right, so that's bit 1, 2, 3, 4, 5, 6, 7. That's enough. Now back to parallel mode. So then it's allowed to make another write. Now we don't really have anything protecting these things from colliding. It's just statistically it's probably not going to happen because it's only every 3 seconds. So let's try that. Fingers crossed after all of this. We actually get our SPI register to work. All right. Got a single blink. Let's see how I did on my print statement here. Okay, so it's reading. Yeah, so it shifts everything every time it does it. And it's feeding in zeros, right? Because Mossy is low. Looks like it might have worked. Let's see. It's hard to keep track. Just let it finish and then go back and look at it. So the last thing it wrote was F. Things are happening. It's just not very easy to see what. I really don't want these here. We can just, oh, you know what? It's backwards because it's bit 0 through 7. Give it one last shot here. Might be a little bit easier to read, and we can actually it is able to get the data back out. So the parallel writes appear to be working. And data is changing. I don't know if 3 seconds is slow enough for me to make sense of everything, but okay. See, the last bit was still stuck in there. I mean, it was being output. So I might not actually be clocking 8 times. But I'm clocking bit 7 into bit 0, and then I'm letting a parallel write happen. Bit 7 into 0, and letting a parallel. So I'm not actually doing an 8-bit. So this is the, okay, so let's try it now. So 0, 1, 5, 8A. Let's try it one more time, see if we get the same exact values. Because part of it is I don't have any. I'm just statistically hoping that they don't collide. I'm getting the same exact values. So, not sure exactly what's going on there. My bit banging is probably extra sloppy. Well, it is extra sloppy. Probably not working exactly right. It seems to somewhat be working, but anyway, I'm gonna call it a day. I gotta run. We got some things kind of working. So, we actually have a serial parallel register. Probably using about 25 macro cells. How many? Oh, only 21. That's interesting. Anyway, we've got a serial parallel register. We created a clock signal for this SPI register. Either the ESP can clock it with its GPIO 0, or if there's a write to 5000 from the CPU, that'll toggle the clock as well. So this is just an ORing of those two signals. And then on the negative edge, the falling edge is when either if so this is the ESP controls whether or not a parallel load is allowed. So if ESP has that pin high, then this 6502 can actually make that right. Parallel load. Otherwise, that clock we don't actually have an enable. The ESP just either provides the clock or not. So then that shifts our data. Bit 7 comes from the ESP 1, and then bits 6 through 0 were what the previous register had for 7 through 1. So that shifts everything. And yeah, I don't know exactly. We tested it out, and the INL Retro is able to write and read back from the so it's able to make parallel writes and reads. Our bit banging of the SPI register needs some work. It is getting data in and out, but doesn't look exactly right. So I'm not sure. I don't even have a loop here. We need a smarter bit banging loop here, but we got some bugs to sort out there. But we are moving forward and have a very rudimentary SPI register. It's not completely working, but anyway, yeah. So we'll figure out what's going on there next time. And yeah, so thanks all for tuned in, and won't be around next week with the holidays and everything, but we'll be back the week after that. So